Welcome back to the deep dive. We are taking that fire hose of information out there, all the research papers, the architectural breakthroughs, the internal engineering notes, and we're distilling it down to what you really need to know.
And if you've been following the AI space for, gosh, the last year, you know we are living squarely in what everyone's calling the year of agents.
It really is. It's the shift we've all been waiting for.
It is. We're moving way past these simple Q&A chat models. We're talking about operational AI now.
So autonomous systems that can actually perform complex, multi-step tasks.
Yeah, and sometimes running these workflows for hours on end entirely on their own, interacting with the real world through tools. The LLM is, it's driving the whole process.
But here's the thing. If you, the listener, have ever tried to build one of these or even just use one of these truly advanced agents, maybe you're setting up a workflow for your team or trying to automate some heavy research synthesis, you hit this immediate and totally baffling paradox.
And it is a huge productivity killer.
The longer the agent runs, the worse its performance gets.
It's like watching a marathon runner who's just perfect for 20 miles, and then all of a sudden they hit a wall, they forget the plan, they start tripping over their own feet.
It's a crisis of working memory.
Exactly.
We saw prompt engineering emerge as, well, it was the first discipline on how we talk to the model right after ChatGPT came out.
Right.
But our topic today, context engineering, that really exploded around May 2023, and it's directly correlated with this market need for long-running autonomous agents.
And the reason this whole discipline popped up is purely technical. Agents, by their nature, use tools in an autonomous loop.
Okay.
They decide on an action. They call a tool like a search engine or a file writer. The tool runs, and it generates an observation. That's the detailed result of what it just did.
And that observation, which can be massive, like
down.
10,000 words of web search results, gets immediately and permanently appended right back into the context window, into the agent's working memory.
For future use, exactly. This leads to what engineers quickly realized was an unbounded explosion of messages.
We're not talking about just 4 or 5 turns here.
No, not at all. Companies running these agents in production noted that even, a modest task often requires around 50 tool calls.
50, wow.
And the really large-scale ones, like the ones Anthropic talks about, can span hundreds of turns. That's hundreds of these token-heavy observations just flooding the working memory.
And the consequence of all that data piling up.
It's what researchers have called context rot.
Context rot.
It's a severe kind of cognitive overload for the LLM. The performance just tanks as the working memory grows, and it overwhelms the model's ability to focus on what it needs to do next. It loses the thread.
So context engineering is the direct response to that.
It is. We can define it as the delicate art and, I guess, science of filling that context window with just the right information needed for the very next step.
So you're proactively fighting that message explosion.
You're deciding what's vital, what can be compressed, and what has to be offloaded entirely. It's really the ultimate memory management system for operational AI.
So our mission today is to unpack these essential battle-tested techniques, offloading, reduction, isolation, and really dive into the nuanced, production-ready lessons from systems like Manus, a company that's really pushed the boundaries here.
And ultimately, we want to understand why, at the end of the day, simplification, not more complexity, is the real goal of context engineering.
Okay, let's unpack this. If you are building or using agents today, there are really 5 major themes that developers are using right now to fight this context rot.
And that's a key point. These aren't just academic ideas. These are implemented, battle-tested solutions.
And they're not used in isolation, right?
Rarely. They form this complex, interwoven memory architecture. The whole design is to treat the agent's working memory, that context window, as a finite, multi-layered resource that you have to manage surgically.
Let's start with the first one, context offloading. This feels like the most intuitive concept, doesn't it? It's kind of like separation of concerns or using external storage for massive files.
That is the perfect analogy. The core idea is don't let all your context live permanently in the LLM's message history, especially not the token-heavy stuff.
Right.
If you generate a massive document, a huge web search result, or some long script output, you send it somewhere else. You offload it outside the main context window.
So instead of feeding, say, 5,000 tokens of raw search data back into the history turn after turn, you just send a minimal reference, like a link or a file name.
Exactly that. The most common production-ready way to do this is using a file system.
Just a simple file system.
Yep. You dump the massive output to a file, a temporary text or JSON file, and then you send only a tiny reference back to the agent in its history. That reference might just be observation, file written to workspace results search summary, 1 JSON.
That's a huge token saver.
Yeah.
The agent can then reference the full context, but only if it needs to retrieve it later. That payload isn't just sitting there consuming the budget.
It's only brought back when necessary. And it's pervasive because it just works. Manus uses it all the time, so do deep agents, open deep research, Claude Code.
It's fundamental.
For any production system that's designed to handle real-world data and autonomy, this idea of offloading to an external retrievable file system is fundamental. You treat the context window like your scratchpad, and the file system is your persistent storage for that session.
Okay, so the next strategy is context reduction. How is this different from offloading? Because they both sound like they're reducing the token count.
Right. Offloading is moving the full piece of information out entirely. Reduction is about compressing or summarizing the information that has to stay in the context window.
Oh.
It's the step you take when you look at a tool's output and you think, okay, I need to know the result of this action, but I don't need the 10,000-word transcript of how it happened.
So instead of moving a whole document out, you summarize it, keep that summary in the context, and maybe just discard the raw, verbose stuff.
That's one way. Common mechanisms are summarizing tool call outputs, which Open Deep Research does a lot in its scoping phase, or just pruning old, clearly irrelevant messages entirely.
And we're seeing this get adopted by the big players, right?
We are. It confirms the strategy. For example, Claude 4.5 now supports pruning tool calls and their outputs right out of the box in its SDK.
So the platform providers are basically admitting this is a core architectural need, not just some application layer hack.
Exactly. And we see Cloud Code implement something they call a compaction feature. It kicks off this reduction process when the context window hits a certain percentage, well before the hard token limit.
Because the performance degradation starts early.
It does. We'll talk more about those critical thresholds later when we get into the specific numbers from Manus.
Okay, so if we offload context with strategy 1, we now need a solid way to bring it back when the agent needs it. This brings us to retrieving context, and I know this is where the architectural debate really heats up.
It does. How do you find that offloaded information quickly without adding a ton of latency?
This is the great debate in agent architecture today.
It is. And broadly, you have two dominant camps.
On one side, you have the projects that favor indexing and semantic search. So that this would be using vector stores to index all the offloaded context, the documents, the research notes, and then using embeddings to retrieve context based on the meaning of what the agent is trying to do.
Right, and that approach, which is used heavily by systems like Cursor, is excellent for long-term memory or deep knowledge bases or static documentation. It's really powerful for finding conceptually related ideas.
But then you've got the other camp, systems like Manus and Cloud Code, which are operating these ephemeral sandbox environments. They often prefer just using the local file system and simple search tools.
Tools like glob for pattern matching file paths and grep for string searching inside files.
And this preference comes down to a fundamental constraint, right?
Yeah.
Latency and setup overhead.
That's it.
Wait, let me make sure I understand this. Aren't vector stores always better? I mean, semantic search is superior to keyword search, isn't it? Why would you rely on old-school tools like grep?
That's the critical piece of architectural friction. Yes, vector stores are amazing for finding conceptually related ideas in a large, stable knowledge base. But in an agent sandbox environment, which gets spun up really quickly for a single session, maybe it only exists for 10 minutes or an hour, you just don't have the time or the latency budget to build a complex index on the fly.
So indexing hundreds of files that were just generated in a long session adds way too much overhead.
It's unacceptable overhead. So relying on glob and grep is a practical decision. The agent knows where it put the data. It has the file path from the offloading step, so it just needs fast tools to confirm the file's there with glob, or quickly pull out a specific line with grep.
It's deterministic.
It's deterministic, it's fast, and it relies on standard Linux utilities that are already in the sandbox. Zero setup.
So for retrieving context that the agent just stored in this session, deterministic search often beats semantic search on the metrics that matter most in production: speed and reliability.
Exactly. You're trading some semantic flexibility for immediate architectural stability and speed in a really volatile environment.
That makes the trade-off so much clearer. Okay, moving on to context isolation. This is where we shift into multi-agent setups.
Right. If the task gets too complex, instead of building one massive agent that tries to hold the entire history of a project, you split the cognitive load. You use multiple agents or sub-agents to enforce that separation of concerns.
So if I'm understanding this right, context isolation is kind of like breaking a huge project team into smaller, dedicated task forces, like a research team, a coding team, a writing team, so no one person gets overwhelmed with all the meeting notes.
That's the perfect human analogy for it. The core benefit is that each sub-agent gets its own, much smaller, dedicated context window.
Right. The researcher only cares about search results.
And the writer only cares about the synthesized outline and the final style guide. They don't need the entire debug log from the code executor agent. By limiting what each agent sees, you dramatically reduce context rot in their individual working memory.
And this is widely adopted in production.
It is, for that exact reason. Manus wide agents, Open Deep Research, Claude's multi-agent researcher, they all use this structure to keep context surgically scoped and manageable. It's a core design pattern for complexity.
And finally, a key trick Manus noted that often goes with retrieval and offloading: caching context.
Caching is just the idea of reusing previous computation results to save both token space and latency. It's often tied really closely to knowledge management.
So if the agent had to calculate something 50 turns ago, it shouldn't have to reread the input data or recalculate it.
Right, not if that value is cached and quickly retrievable. It's making the agent's prior work immediately available rather than forcing it to rederive the answer from its history. And that cache can be used as a condensed form of memory that enters the context window as a structured summary. It's a shortcut.
Okay, to make this really concrete for everyone listening, let's connect the dots. Let's use the example of Open Deep Research and show how these 5 strategies might all weave together in a single workflow.
Yeah, Open Deep Research is a beautiful illustration of this architectural choreography across its phases: scoping, research, and then the final writing.
So during that initial scoping phase, the agent defines the research plan.
Which is crucial. It's the agent's objective function. But critically, it immediately offloads that plan.
It saves it independently so it doesn't get lost in all the noise.
Yes. It saves it as a file so the agent doesn't lose sight of the original goal amidst the inevitable token explosion of the research phase that's about to happen.
And then during that heavy research phase, the token-heavy observations flow back from the search tools.
And here, the system uses reduction by summarizing that observation before it gets appended to the history.
And it achieves isolation by using subagents for different parts of the research.
Which ensures each agent is operating within a manageable, focused context window. Then the agent might use retrieval so, glob, or grep to pull that original research plan back into the context during the final writing phase, making sure the final output sticks to the initial goal.
And if a calculation needed to be done multiple times,
The system might use caching to quickly access the results without recalculating. It's a multi-layered defense against context rot.
that sets the stage beautifully for the hard-won lessons from the field. Manus, in particular, has been forced to iterate and refactor their agent architecture so rapidly, and they've shared some incredibly fresh, battle-tested insights, especially focusing on what they call the discourage column, the ideas that are often non-consensus or, kind of counterintuitive.
What's so fascinating here is that their biggest breakthroughs didn't come from following the standard industry advice. They came from realizing where that conventional wisdom was actually leading them astray.
Let's start with the philosophy. Why context engineering now? Manus argues that a startup or a developer should lean on general models and context engineering for as long as possible. Why avoid building specialized models so early?
This came from years of painful experience in the NLP space. They realized that trying to solve the open domain problem, giving an agent the ability to tackle any task a user throws at it by building specialized models, is a trap. It just leads to a massive resource drain and really slow movement.
What were the specific pitfalls they ran into?
So, trap 1, training specialized models from scratch. They noted that even with smaller models years ago, a single training and evaluation cycle could take 1 or 2 weeks.
A week or two.
Yeah.
For one cycle.
Think about that iteration speed. If you are pre-product market fit, that is a death sentence. You risk spending all this time and money optimizing internal benchmarks that might not even correlate with what your customer actually values.
So context engineering, which is all done at the application layer with general models, gives you dramatically faster iteration cycles.
Absolutely. You can deploy and test a new context management strategy in an hour, not a week.
And then there's trap 2.
Trap 2, fine-tuning the LLM using reinforcement learning, or RL, which is often cited as the next frontier for agent intelligence. Manus found this to be dangerous because the AI landscape just shifts too quickly.
That's a really strong claim. Why is RL fine-tuning dangerous here?
Because if you fine-tune with RL, you're typically fixing a specific set of tools, an action space, and you're designing a reward system around your current product. But look what happened when the Microsoft Code Interpreter, the MCP, launched.
Right.
It forced a paradigm shift from a compact static action space to an infinitely extensible one where you can run any shell command.
And if you just spent months fine-tuning your model to use that old compact set of static tools, that entire investment is basically invalidated overnight. The fundamental tools have changed.
Exactly. Trying to optimize these open domain problems with RL basically means you are trying to become an LLM company yourself. You're constantly duplicating the costly and rapid foundational work that Google, Anthropic, and OpenAI are already doing.
So the core realization is that context engineering is the clearest, most practical boundary between application development and model development.
Right. Stick to the application architecture and let the foundation model builders focus on the foundation. Trust your choice, they say. Use the general models and just manage their context meticulously. That's where the defensible IP and the iteration speed are.
That is a powerful lesson in resource allocation. Now let's dive into the really deep nuance of context reduction. Compaction versus summarization. This isn't just about making text shorter. It's about maintaining the agent's history and ensuring reversibility.
This distinction is so crucial for maintaining state. They classify context reduction into two operations, and compaction is always preferred.
Okay, let's nail down the definition of compaction first.
Compaction is the reversible process. It strips out information that can be precisely reconstructed from the external state, which, for Manus, is the file system.
Okay, so give me an example.
Let's take the file write tool. The full tool output message would include the path and the full lengthy content that was just written.
And that content could be 1,000 tokens.
Easily. Once that write is complete, the compact version safely drops that token-heavy content field and just keeps the path. The agent just sees, file written successfully, path.resultsoutput.txt.
So no information is actually lost. It's just externalized and referenced. You're maintaining the history of the action without the token overhead. Why is that reversibility so critical for these agents?
Because agents do chain predictions. They need to base step 100 on something they saw at step 5. You just never know which past action might suddenly become super important later on, like realizing a dependency on a specific file created way earlier.
And if you irreversibly summarize that action, the crucial file path might be gone forever.
Compaction avoids that risk entirely. Which brings us to summarization. That's the irreversible approach.
And they only use that when?
Only when the gains from compaction are tiny. And even when they do summarize, they often offload the key parts of the context first. Sometimes they'll just dump the entire pre-summary context as a detailed blog file into the file system, just in case the model needs to retrieve that raw history later with glob or grep.
So they have this highly structured process that's triggered by performance metrics. Can you walk us through that process for triggered reduction at Manus?
Yeah. First, they had to move past just thinking about the hard token limit and identify what they call the pre-rot threshold. So a model might have a hard limit of, say, 1,000,000 tokens, but they found degradation context rot, repetitions, worse reasoning, hallucinating actions. That starts much earlier, typically around 128K to 200K tokens.
So 128K isn't the failure point. It's the point where the agent starts making sloppy mistakes because it's cognitively overloaded. And that's the trigger.
Exactly. The moment they approach that pre-rot threshold, they trigger context reduction, and they always start with compaction. But they don't compact everything.
Right.
They compact the oldest 50% of tool calls, and they keep the newer ones, the most recent 50% in full detail.
Why that deliberate split? Why keep the newer history totally intact?
To avoid a phenomenon they call imitation. If the model only sees these compact, incomplete outputs in its history, just the file paths, for instance, it might start imitating that behavior and output its own actions in a compact format with missing fields.
Which would be totally wrong or unusable by the next tool in the chain.
Right. It needs fresh, full detail examples of how to use the tools properly and what the full expected output should look like.
That is a subtle but absolutely critical behavioral insight. And if the gains from compacting the oldest half are still small, then they'll proceed to summarization.
Right, but again, with vital constraints. First, you always use the full version of the data for the summary, not the already compacted version, to ensure high recall of the details. And second, even after summarizing, they still keep the last few tool calls and results in full detail
Why is that?
to maintain continuity. The model needs to know precisely where it left off, what the immediate environment looks like, and what its last successful action was before it can continue smoothly.
This is so much more than simple memory pruning. It's a highly structured, tiered memory management system.
It is. Now let's turn to isolation and coordination. Manus strongly agrees with the warning against over-engineering multi-agent setups. They call complex coordination a nightmare.
Why a nightmare?
Because information syncing is a classic computer science coordination challenge. It's similar to the problems you face in multiprocess programming.
That echoes the famous maxim about concurrency. Do not communicate by sharing memory. Instead, share memory by communicating. It sounds like they just translated memory to context.
They did, and they used two distinct patterns based on that idea. First is pattern 1, by communicating. This is the classic subagent.
Okay, describe that setup.
This is the simpler approach. The main agent sends a clear instruction, and the subagent's entire context is only that instruction, its system prompt, and its specialized tools.
So it's used when the task is short, clear, and only the final output matters.
Exactly. The main agent doesn't care about the subagent's internal struggle or intermediate steps. Like when Claude Code delegates a search for a specific function in a massive code base, the main agent just wants the result back. It's fast, it's clean, and the context windows are minimal.
And then there's the other pattern.
Pattern 2. By sharing context memory. This is for the deep research or complex debugging scenarios where the full history is vital for the subagent to maintain coherence.
So in this pattern, the subagent sees the entire previous context, the full tool use history, all the intermediate notes.
Yes. And while you could force the main agent to save everything to files and make the subagent read them, that just adds a ton of latency and token cost.
So you bite the bullet and share the context.
You do. But this comes with a severe trade-off that developers often forget about: KV cache reuse.
Wait, can we pause and define that for the listener?
Yeah.
What is the KV cache and why is it broken by sharing context like this?
Okay, so the KV cache, or key value cache, is a critical piece of infrastructure in modern LLMs. When you feed a long prompt, the context window into the model generates key and value vectors. This is the memory representation of that input.
And computing those is very costly.
Very. The KV cache is the part of the GPU memory that stores this costly computation, so the model doesn't have to recompute the entire prompt on every single token it generates next.
So if I ask the model 20 questions in a row, it only computes the input text once and uses those cached vectors for the next 19 answers. Saves a ton of time and money.
Correct. But if you launch a subagent with pattern 2, even if the history is identical, the subagent has its own specialized system prompt and action space, because the entire initial input has changed, even just slightly.
The KV cache infrastructure often can't be reused.
Exactly.
I see the financial implication now. It means every time you launch that subagent, you are paying the full price for that context prefill all over again.
You're essentially paying double or triple for the same history. It increases your input token cost, making pattern 2 way more expensive and latency heavy than pattern 1. It's a trade-off. Coherence at the cost of computation.
And to manage the output of these isolated agents, Manus uses this advanced coordination trick, the agent-to-agent communication trick, or agentic MapReduce.
This is where they impose structure on the chaos. When the main agent spawns multiple subagents, say 10 simultaneous research tasks, the main agent has to define the precise output schema, the date contract for the result.
What does that contract look like?
It could be a specific JSON format or, say, a spreadsheet layout. The subagents then use a special tool, submit result, which uses constrained decoding to make sure the result conforms exactly to the main agent's schema.
Can you elaborate on constrained decoding? That sounds highly technical.
Constrained decoding is a technique that limits the tokens the LLM can generate next to only those that form a valid structure, like valid JSON, based on a predefined schema.
So instead of the model just generating free-form text,
The main agent dictates your output must have a summary field, which is a string, and a confidence score, which is a float.
that is so critical. It prevents the main agent from just getting 10 paragraphs of unstructured prose from 10 different subagents. It forces the collective output into a controlled, structured data output, like a spreadsheet with fixed columns.
Which is ready for the main agent to synthesize. It's the essential tool for turning multi-agent collaboration from just an information exchange into a real data processing pipeline.
Okay, here's where the architectural discussion moves beyond just memory management to how the agent actually interacts with its environment. Manus realized that the tools themselves are a massive contributor to context explosion.
Mm-hmm.
And it leads not just to context rot, but to context confusion.
Context confusion is when the model starts calling the wrong, irrelevant, or even non-existent tools because its working memory is just cluttered with old, deprecated, or context-specific tool definitions.
I can totally see how that happens.
Yeah.
If you define 50 tools in the system prompt, that's 50 functions, arguments, and descriptions the model has to perpetually carry in its working memory, even if it only needs 5 of them for the current task.
And the typical solution dynamic or on tool descriptions loading tools on demand is problematic.
Right, as we discussed, dynamic loading breaks that precious KV cache.
And worse, if you remove a tool, past calls to that now removed tool are still sitting in the context history. That confuses the model into trying to call an invalid tool based on its memory of past actions.
So the solution is not to dynamically load the tools, but to abstract and offload them through a 3-tiered tool offloading system. This keeps the core interface simple while allowing for infinite extensibility.
Right. Let's break down these 3 layers of abstraction from the core outward.
Let's do it.
Level 1 is function calling, or atomic functions. This is the smallest, most stable core layer. Manus keeps this fixed and tiny, maybe 10 to 20 carefully curated atomic functions.
And what qualifies as atomic in this system?
The basic low-level operational primitives. Reading and writing files, executing generic shell commands, searching the internet, or essential browser operations. They're highly composable, and crucially, they're schema-safe thanks to constraint decoding. The model can't easily call them incorrectly.
So the model's core vocabulary is small, stable, and predictable. And that stability is the key. Now, what does that stability allow them to offload to level 2? Sandbox utilities, the command line.
This is the smart bridge. Since every Manus session runs inside a full Linux VM sandbox, they offload a massive amount of capability to the command line environment.
So these are pre-installed, custom-developed utilities.
Yeah, format converters, specialized speech recognition processors, or the crucial MCP CLI for complex coding tasks.
So the agent doesn't have a specific resize image tool defined in level 1. It uses the atomic shell command tool, and then inside the shell, it calls the external image resizer utility that lives in the Linux environment.
Precisely. Let's trace that. Imagine the user wants to convert a massive XML file to JSON. The agent doesn't need to know the entire XML to JSON tool definition. It simply decides, I'll use shell command and run a surbin XML to JSON with the right input and output flags.
That is genius because it lets them add new, complex capabilities extensibility without ever touching the model's core function calling space. It keeps that level 1 interface cache-friendly and stable.
And furthermore, these level 2 utilities can write large outputs directly to files or return results in pages, leveraging standard Linux tools like grep, cat, or less for on-the-fly processing and reduction before the output even hits the LLM's context.
It's a trade-off though, right? Shell interactions aren't always ideal for low latency, back-and-forth stuff with the user interface.
Correct. You trade off some front-end responsiveness for architectural stability and massive flexibility. It's a calculated cost. And the final, deepest layer is level 3, packages and APIs or scripts.
This sounds like the layer for the really heavy-duty, computation-intensive work.
It is. This is where Manus writes specialized Python scripts to call pre-authorized external APIs, financial data providers, complex 3D libraries, specialized machine learning endpoints.
Why use a script instead of just calling the API directly with a level 1 function?
Because these tasks are often computation heavy and they generate enormous amounts of raw data. Think about analyzing a year of stock data. You do not feed the model all those numbers.
Right.
You let the script crunch the numbers, generate the key insights like top 5 movers, and you only put the synthesized summary back into context.
So the script acts as this powerful external filter and computation engine. And how does the agent even access this layer?
It leverages the level 1 atomic functions again. It uses the atomic file function to write the script, script.py with the necessary computation. Then it uses the atomic shell function to execute that script, Python script.py.
It's like the code act concept, where you bundle complex computation into a single, high-value, auditable step.
It is.
So if I'm getting the grand design here. From the model's perspective, the part that's actually consuming the context, all the complexity, all the new capabilities, all the data processing, it all still flows through the same simple, fixed set of level 1 atomic function calls, mostly shell and file I/O.
That is the core insight of context engineering applied to the action space. It keeps the model's interface simple, highly cache-friendly, and orthogonal. The complexity is managed externally in the sandbox and script layers, protecting the LLM's working memory from getting cluttered with tool definitions.
It's a brilliant realization that tool offloading is just as important as data offloading in the fight against context rot and confusion.
Absolutely. And as we noted earlier, these layers are all interdependent. Offload and retrieve enable efficient reduction. Stable retrieval makes isolation safer. The tiered action space significantly reduces the need for constant context reduction because the tool definitions are stable.
So context engineering, at the end of the day, is a constant balancing act of all these conflicting objectives.
It really is.
We've covered the architectural strategies and the specific, often counterintuitive lessons from Manus's development. Let's synthesize these insights into practical architectural decisions that listeners can actually apply, starting with practical architectural decisions.
We should revisit the retrieval choice, specifically their decision to avoid indexing databases or vector stores for context retrieval within a sandbox session.
I'm still surprised by that avoidance given the current hype cycle around vector databases. Why is it such a firm decision for them?
Because their primary use case involves these ephemeral, time-limited, totally novel sandboxes. If the agent generates 50 files in 5 minutes, the latency involved in building a semantic index on that new data, loading it, and then querying it, it just doesn't compete with the speed of file system operations.
So for retrieving context generated within the session, the cost-benefit ratio tilts heavily towards simple file search.
Towards deterministic tools like glob and grep. So vector stores are great for global knowledge bases, but not for local, transient, working memory retrieval.
And that choice then dictates their preference for specific data formats.
Absolutely. They prioritize line-based formats, plain text, CSV, structured logs, because that lets them use those simple, powerful Linux tools like grep to read line ranges or search for strings without loading the whole file. And they also noted a minor but important detail. They favor plain text over heavy markdown formatting.
Why avoid markdown?
They observed that if the context history contains too much markdown, some models can start imitating that style, sometimes outputting, excessive unnecessary bullet points or structure that just clutters the final output.
So for operational data, consistency and machine readability win over decorative formatting.
Every time.
We stressed the importance of structured output earlier, but let's focus again on summarization quality. You mentioned avoiding free-form summarization.
This is a huge quality control issue. Manus found that if you just prompt the LLM with summarize the last 50 steps, the output quality is all over the place.
It's too variable.
Totally. So instead, they define a structured schema or a form with fields for files modified, key insights, user goal progress, where the agent left off, and they force the AI to fill that form using constrained decoding.
The structure acts as a tight contract. It forces high recall of specific crucial metrics while dramatically stabilizing the summary's output quality.
Exactly. The human analogy is, don't ask a student to write an essay on the class. Ask them to fill out this form detailing topic A, supporting evidence, and 3 open questions. The structure ensures you get what you need.
And a crucial point on the philosophy of just surviving in this space, model agility. Manus launched in March and had refactored its core architecture 5 times by October. That rapid evolution is exhausting, but it's necessary.
It speaks to the volatility of the field. The best practice they established is to fix the core agent architecture, the context engineering strategies, and then proactively test its future-proofness.
And how do they do that?
By switching between strong and weak models.
So switching, say, from the current flagship model to a slightly older, less capable one, or even an open source model.
Great. If the new architecture still gains significant performance from the stronger model, it provides an early signal that the design is robust and not just relying on some specific proprietary model's hidden strengths. It means the architectural foundation is strong enough to weather future model changes.
Okay, moving on to agent infrastructure and memory. How does Manus handle true long-term memory across sessions? The stuff a user wants the agent to remember forever.
They handle this using explicit memory, which they call knowledge. And crucially, it is not automatic. The agent observes patterns like the user always wants results in Excel format. It then proposes saving this insight. The user must then explicitly confirm, via a dialog prompt, that yes, the agent should remember this preference for all future sessions.
That prevents context pollution. Only verified, user-sanctioned preferences enter the long-term memory store.
Precisely. It's memory governance. They also keep their multi-agent structure incredibly simple. We noted they avoid that human org chart analogy. They don't have a designer or manager agent.
And why is that human role analogy so problematic?
Because it forces an analogy that makes communication difficult and rigid. Humans have implicit communication norms. Agents need explicit, structured contracts.
So they stick to very few broad agents.
A general executor, a planner, and a knowledge management agent. And the planner, notably, is implemented as an agent as tool with a separate, unencumbered perspective for external reviews of the current state.
The agent as tool concept is fascinating. It's like giving the main agent the ability to pause and consult an external objective advisor who isn't burdened by the main agent's working context.
Yes, the planner sits outside the main execution loop, allowing it to objectively analyze the history without the cognitive pressure of having to generate the next action.
Okay, let's talk money. Model choice and cost. Manus made a surprising find. Flagship proprietary models can actually be cheaper than self-hosting comparable open-source solutions at scale. This goes against the common perception that open source is always cheaper. Why the counterintuitive cost analysis?
It comes back to the KV cache, which we defined earlier. When you are running a real long-running agent, the input context is almost always much longer than the output. You spend massive resources pre-filling that large context window, the input cost, before the agent generates the next token, the output cost.
So if you self-host an open source model, you are bearing the full infrastructure cost of constantly recomputing that context prefill if your cache management is inefficient.
Exactly. The flagship providers Anthropic, Gemini, OpenAI, they have distributed highly robust and hyper-optimized KV cache infrastructure baked into their offering. This optimization is crucial for cost control when you're dealing with extremely long context windows.
So Manus routes tasks to the best model for the job.
Claude for coding, Gemini for multimodal, OpenAI for math and reasoning. They optimize for capability and cost on a per-task basis. That means proprietary infrastructure can monetize context efficiency, which is a powerful advantage over self-hosted models, even if the token price seems higher on the surface.
It fundamentally changes the economic equation for agent builders.
It does.
Finally, let's talk limitations and future challenges. Building these complex systems comes with significant challenges, especially around safety and guardrailing.
Anytime you connect a sandbox to the internet, especially with a browser tool, safety becomes incredibly difficult. The system needs to perform rigorous checks. Manus implements strict controls on outgoing network traffic. For instance, preventing tokenized data, like sensitive internal prompts, from leaving the sandbox environment in case of a prompt injection attack. The system acts as a firewall, watching what the agent is trying to send out into the wild.
And that's often not enough.
Not at all. Any sensitive operations like persisting a login, accessing personal data, initiating a transaction require manual user confirmation. It's a progressive approach where the user often has to take over if the operation is deemed too risky.
And what about evaluation? How do you even measure success in such an open domain system?
The public academic benchmarks like Gaia are often misaligned with real user satisfaction. They measure narrow skills. Manus realized their gold standard has to be simple. The user's 1 to 5 star rating on a completed session.
The user get what they wanted?
That's it. But even user ratings are insufficient for nuanced outputs, like design.
Right.
So they still rely heavily on human interns for taste-based evils, particularly for outputs like a visually appealing website, or creative tasks that a simple reward model just can't judge accurately. The human eye is still the final arbiter of quality.
And the future of reinforcement learning in this space seems, well, stalled.
It is, particularly for systems supporting these infinitely extensible action spaces, like when you integrate the MCP. Standard RL with verifiable rewards becomes impractical. It's too hard to design a stable reward model and generate balanced rollouts across an effectively infinite set of possible actions.
The action space is just too vast to explore systematically.
Yes. The field needs to focus on parameter-free online learning methods, like leveraging collective user feedback and common corrections to achieve self-improvement. Let the wisdom of the crowd signal what needs adjustment, rather than trying to map every outcome with a hand-tuned reward function.
So the ultimate low-effort RL signal is just watching what users repeatedly correct.
It is. And if we connect this to the bigger picture, the most enduring lesson for Manus, looking back over all their rapid evolution and refactoring, is maybe the most provocative insight we've covered today.
Which is?
The biggest leaps in performance, in stability, in efficiency, they didn't come from adding fancier retrieval hacks or more complex multi-agent layers. They came from simplifying or removing unnecessary tricks and complexity at every single architectural layer.
So what does this all mean for you, the learner, the developer, or the curious user? The entire goal of context engineering, all the offloading, reduction, and layering, it isn't to make the LLM more powerful. It's to make the LLM's job simpler.
To make its working memory as clean and uncluttered as possible.
The biggest takeaway is to avoid context over engineering. Build less and understand more. And this changes how we should approach the AI tools we use every day. We should seek out tools that prioritize simple, stable core actions and aggressively externalize complexity, rather than those that try to cram the entire world into a single, massive system prompt.
Look for the simplified, layered architectures. The token count is no longer just a cost metric. It's a proxy for architectural health.
That's a wrap on our deep dive into context engineering.